Way too much more of your time.
Okay, so this lesson's 9.3, which is geometric sequences and series. And I think on the assignment there are three problems that are geometric. So the other two are arithmetic, yeah. So a geometric sequence is where you have constant ratios. So in arithmetic, you're adding the same thing. Geometric is you're multiplying by the same thing. So you're multiplying each term by the same number, and that gets you your next term. So the ratio between each term is the same. So if you have your sequence of numbers, if you take a number, divide it by the previous term, and you do that each time, you're going to get the same number, and that's what makes it geometric. So if they're not the same, then it's not geometric, and then it's usually arithmetic, or it could be something else. So I'm going to just demonstrate this with three different sequences. Get my pen out here. So the first one here, we have 5, 10, 15, 20. So you would be taking each term divided by the previous term. So like out of 5 and 10, you'd have 10 divided by 5, which gives you 2. And then you go to the next pair, 15 divided by 10. That gives us 1.5. So those are not the same. So because these are not the same, these are not geometric. And in fact, this particular sequence is an arithmetic sequence because you're adding 5 every time. So you can see that just by looking at it, that, oh, I'm just adding 5, so it's not going to be geometric. But you can verify that by checking the ratios. So this is, in fact, arithmetic. Now the next one here, we've got 27, then -9, then 3, then -1, and then it keeps going. So always be careful because you want to do the second term divided by the previous term, because I look at this and I'm like, oh, 27 divided by -9, but that's not what we're doing. We want to do -9 divided by 27. And this is going to give us decimal, so I'm going to just leave it as a fraction so that way you can see whether you are actually, converting it correctly or make sure that the fractions are the same. But this gives us -1/3.
Sure.
So then I'm going to take the next pair, which will be 3 and -9.
-1/3.
That gives you -1/3. And then you should always double check to make sure. And yeah, we get that -1/3. So our constant ratio here is -1/3, so that makes this geometric. Now, something I've seen a lot of people do is they'll make them decimals, and then they'll see decimals that are close to each other but are not equal, and then they'll say, oh, this is geometric. But or they'll be like adding the same number each time, or they'll be adding something and it's almost adding the same number every time, but it's not, and then they'll say it's arithmetic. So it's they need to be exactly the same. So you can't just say, oh, they're the same if I round, but like to 1 decimal place or something like that. You want them to be exactly the same. So you want to watch out for that. Now the third one here, so we've got 5, 1, 0.2, 0.04. So we're going to have 1/5. So of course that's 1/5. And because I have decimals, I'm going to just divide that because I'm going to be comparing decimals here anyway. Then I have 0.2 divided by 1, which of course is 0.2 again. And then just to verify, 0.04 divided by 0.2. And I am really bad at doing decimals in my head, so I always rely on a calculator for this. That also comes out to 0.2. So our constant ratio here is 0.2, and so again, this is geometric. So it's pretty straightforward. Going back to the rounding thing, I point that out because that first one there, if you rounded the 1.5 to 2, you would say, oh, they're the same, but they're not. So you don't want to round these. You want to look at what it exactly comes out to. Any questions so far?
Nope.
Okay. So now this brings us to the actual formulas. And this is where people get tripped up. Because, and I'm going to highlight this. The formula has an n minus 1. And usually there's an off by 1 error here. Whenever we have sequences, we always start with n equals 1. So that's why we have an n minus 1 in our exponent, so that the first term would not have that r at all because you'd have an exponent of 0. And so you're left with just your first term. A lot of people see this and they're like, oh, it's an exponential equation. Like when we go back to algebra and we learned about exponential equations. Yes. Now the difference is the exponential equations usually start with 0 and these start at 1. So that's where these things start getting confusing. But you can use one or the other as long as you're consistent about what you're labeling and you're making sure you're labeling things correctly. So if we just have an exponential, it's usually something like we'd say a naught because we start at 0, r to the n. And so that's where our n starts at 0 versus geometric, where we have a1r to the n minus 1, and then n starts at 1. So usually what happens is an off by 1 error. And I think it's problem 4 on the assignment with a depreciation problem. There's usually an off by 1 error here because of this sort of deal. So just going to warn you ahead of time about that. To think about, if you're going to start counting at 0, use the left, use the exponential form. If you're going to start counting at 1, use the form on the right, because otherwise you'll mess up there. So just something to watch out for. So we're going to write the first 5 terms of a geometric sequence. And so we're going to be using the geometric sequence form, a1 times r to the n minus 1 equals a to the n. So a1, a2, a3, a4, a5. So of course we're starting at counting at 1, not at 0. So the first 5 terms goes up to a5.
Sure.
So for the example on the left, I got a1 equals 7, so I can fill that in, and then r equals 4. So a2 is you're just multiplying that by 4. And if you really, we want to use that form, it'd be 2 minus 1 in that exponent. So that's just 7 times 4. So we get 28.
28
so each time, yep, 28 times 4. So you could do 28 times 4 because you know that you're doing the first 5. And doing this on my calculator, that's 112. Otherwise, what you could do is then 7 times, if we're using the formula, then we'd have 3 minus 1, so it'd be 7 times 4 squared, and you'll still get 112. So it's easy enough when you're doing like the first 5 terms, that as long as you know what r is, you can just keep multiplying. But it's good to know the formula, because what if I asked you what is the 100th term? You would not want to do that by hand. You would want to use the formula for that, because or maybe Excel. If you did it in Excel, you could probably do it pretty quickly.
799 minus 1. 100 minus 1.
Yeah. So just for good measure here, because geometric sequences, and this is also something that's a slightly different than with exponential sequences, because geometric sequences can, if I do 1 minus 0, just to show you that with the formula, Geometric sequences can alternate sign. They can go from positive to negative to positive to negative, but exponential equations don't do that. They don't alternate back and forth like that. So that's one of the other differences between something that is exponential and something that's geometric. Because exponential equations, their R is never negative. But if you have a sequence, that's okay. So here it's easy enough. You just multiply each one by 1/4. And because they're giving us R as a fraction, you want to keep your answer as a fraction. So I strongly recommend using some sort of calculator that does fractions, because that just makes your life easier. Oops, and a negative. So you can see we got a negative 3/4 or 3/2. Then I multiply that by our negative 1/4, so we're going to get a positive 3/8. Then we have that 3/8, negative 1/4. So negative 3. Oh, whoa, I put the wrong number on the top.
332.
And then a to the 5th. I don't know what 32 times 4 is. Oops. And then this gives us a positive 3 over
128.
128, yeah. So easy enough. Once you know what the pattern is, it's pretty easy to find the first 5 terms. You know, you don't really need the formula for that. These, you're going to want to need the formula because we're asking for larger terms. The 18th term and the 20th term. And you're not going to want to write 18 of these numbers to then figure out what that is. So you're going to want to use the formulas here. So we have a to the n is a1r to the n minus 1. So they give us everything we need. We just need to literally plug it in. So the 18th term will be 5 times 7/2 to the 18 minus 1. So that's 5 to the 7/2 to the 17. And this is where I rely on my calculator and its ability to work with fractions.
I don't know what calculator you're using.
I'm just using the TI-30X. There's actually a fraction button on there. This comes out to a giant number, which you definitely would not want to have to try to find this without using a formula. I put in all of my, there. So hundreds, thousands, millions, billions. Okay, so that's like over 8 billion for the 18th term. These things get big pretty quickly. So same thing on the right. So this time we want the 20th term. So we're starting with 64. R is 1.02, so it's going to be 20 minus 1. So that's 62 or 64 times 1.02 to the 19. And then calculator comes in handy. 93.2359150. For something like this, because they gave us a decimal with 2 decimal places, I'd usually round it to 2 decimal places just to kind of match. And I'm actually going to cover rounding here because I often see people rounding wrong. So if I have 2 decimal places, it would be 0.23, but because after that spot I have a 5, the rule is you round up if it's 5 or higher. So we will actually round this to 93.24 because the third digit after that is 5. So I see a lot of people forget that rule. You probably haven't used it in ages. So it's pretty simple using the formula once you know how to set it up. Do you have any questions so far?
No, ma'am.
Okay. So now we're going to start getting a little more complicated, where we're going to find the formula based off of what we have here. And actually, I may not even need to do both of these. It seems like it might be overkill. So we know what the first term is because they're telling us in both of these cases, the first number. So for both of these, we know the first term. So A1 is 81 or A1 is 6. Next, you need to find R. So that's where you're going to have to take one of the pairs and then divide them. So R here is going to be 27 divided by 81. And that reduces to 1/3. So once you have that, that's all you need because it says to just find a formula, so you don't have to do anything else. You're just filling it into the formula. So just as a reminder, it's a to the n, or an equals a1 r to the n minus 1. So our formula would be 81, and then r is 1/3, and then n minus 1. So not too bad. All you need is, as long as you know it's geometric, you don't need more than 2 points as long as you know it's geometric. And here we are assuming it's geometric because that's what we're learning about. So here, oops. So the second example, -9 divided by 6, that reduces to -3/2. So we have an equals 6, -3/2 to the n minus 1. I think the n minus 1 might be the biggest thing that people might forget. So they'd rather just put it to n. So here's something that, now these are going to be tricky. So these are going to involve some thinking here. Find the specified term of the geometric sequence. So for the first example, find A1 given A2 equals 3 and A5 equals 3/64. So we're not given R, we're not given A1. All we know is A2 and A5. And we want to know what A1 is. So I'm going to kind of set up, so let's look at the base actually. So we have AN is A1 R to the n minus 1. So if I plug in for n equals 2, I have A2, which is 3, which is A1 R to the 2 minus 1. And that gives me 3 equals A1 R. Now I have another point with n equals 5. So A5 is 3/64. So that's A1 R, and then 5 minus 1. So that gives us 3/64 equals A1 R to the 4th. So we have two equations here, and this is actually a non-linear system of equations. We have two equations here. We want to find A1, so I can take the first equation that I've written, and let's say I solve that for R, so I can plug it into the other equation. So R would be 3/A1. I can plug that into R here, and then that will give me just one variable to solve for, and then I can solve for A1. So I have 3/64 equals A1, and then I have 3/A1 to the 4th power. So this is going to take some simplifying, some algebra here. That exponent of 4, that gets applied to both the 3 and the a over 1, or the a1. So 3 to the 4th is 81. So I'm going to end up with 81. And then I have a1, and then I have a1 to the 4th in the denominator. I can cancel out one of these, and that would leave me with a1 to the 3rd, because one of those a1s can cancel. So we're trying to find a1. This is actually something that I can cross multiply here to solve for, because I have 3 over 64 equals a1, or 81 over a1 to the 3rd. So you can cross multiply. So I multiply one diagonal, because this is a proportion. So 3 times a1 cubed. And then I'm going to multiply the other diagonal, 64 times 81. I'm going to run out of room here, so I'm going to just skip this other example. We'll just do this one. So I've got 3 times a1 cubed equals 5184. I can divide both sides by 3 so that I can get just my a1 cubed. So that comes out to 1728. Now to get rid of a cube, you take the cubed root of both sides. And that is the same thing as taking it to the 1/3 power. So if you don't have a button on your calculator that allows you to do that, you can, it's the same thing as using the 1/3 power. So that's actually usually how I enter it in, as I do it to the fractional power. And that gives me 576. So we were able to determine what a1 was. We had to use the techniques from week 2 where we're learning about those system of equations. We basically did substitution here so that we could solve for our missing variable. Do you have any questions on any of those steps?
No, understood.
Cool. And I'll just skip that other example, but it's basically sort of, the other one's actually easier because you're given the first and the second step. So from there, then you just have to use the formula. So that's fine. Okay, so now the fun stuff is getting to worry the sums of these things. And I love that there are formulas, because otherwise if you had to sum these up by hand, that would just be really hard. So I love that we have formulas to do it for us. So the sum of a finite geometric sequence, so we use our sum formula, and it's Sn, so the S just means sum of the n terms. And we start with our a1, r, and then instead of n minus 1, it's I minus 1. So as long as you start counting at 1, this gives you a1 times 1 minus r to the n over 1 minus r. And this is for a finite sequence, so if you have a stopping point, so you're only counting a certain number of items. So we're going to use that formula here, and I'm going to rewrite it. So our sum, and both of these start at n equals 1. It is a1 times 1 minus r to the n over 1 minus r. Let me verify, yeah, make sure that I wrote that correctly. So the first example on the left, n is going to be 10, because that's the number on top of the sum symbol. And we don't have a number in front of our parentheses that's raised to n minus 1. So A1 is going to be 1. We just assume that's going to be 1. And then R is what's under the n minus 1, so that's 3/2. So once you've identified all this, you just plug it into the formula. And so we're finding the sum of the first 10 terms. So you're going to write S10. So A1 is 1, so I'm not even going to bother writing that. 1 minus 3/2 to the 10th power, or 1 minus 3/2. So it's going to get kind of nasty. I guess I really don't need these parentheses here because the number in front is just 1. 1 minus and 3/2 to the 10. I'm going to just do 1 minus 3/2 to the 10 on my calculator. Let's see, my calculator give me it as a fraction. No, it's not going to give it to me as a fraction. So I will just rewrite it like this. I'll just keep it written like that. But I could do 1 minus 3/2. That's easy enough. That's negative 1/2. So it's perfectly fine to rely on your calculator to do all of this. You don't have to show every step here. So my calculator is just defaulting to a decimal. And it does not want to make it into a fraction at all. It just refuses. It's saying, oh no, I'm giving you decimals. So I'm going to write down the decimal that I'm getting. And then I'm going to pull up the scientific calculator in Desmos because that is a lot friendlier with fractions. Let me just pull it up here. So if I have something that I have to do with fractions, I usually use this calculator because it does it a lot easier. So what's really nice is I can do this whole thing. 1 minus parentheses, I put in another fraction, 3/2. And my exponent, 10. And then I have 1 minus 3/2. So you can see I got the same decimal version, but what's nice is that I can convert it to a fraction. And so that's what the sum comes out to as a fraction. Is
That's
this
handy.
Sorry, go ahead.
That's handy.
Yeah. Yeah, like I'm using my regular handheld calculator, but it can't do this. But Desmos does. And so I would definitely rely on Desmos for these things because otherwise you're just going to get nasty fractions and decimals and all that stuff. So it's 55,802.5 by 512. So if it's going to come out to a nasty decimal, we generally keep it in a fraction form, but it does get pretty gross. So second example here, n is 8 in this case. A1 is 5, and then R is negative 5/2. So we're going to fill in their formula. Sn equals A1, so 5 times 1 minus negative 5/2 to the n. So it's going to be the 8th power over 1 minus R, so negative 5/2. And again, I'm going to not even bother with my handheld calculator. I'm going to just plug it into here because it's just going to be a lot nicer, a lot easier. 1 minus negative 5/2. exponent of 8. And then our denominator, 1 minus negative 5 halves. Oops. So you can see, again, we get a really nasty looking decimal, but we can also convert that to a fraction right here. So I will write.
Really nasty looking fraction.
Yeah, they're both really nasty looking. So, oops. Equal, let's see if I can try to 2178.33984.
3, 8.
Thank you. And then as a fraction, negative 27.
278, 135, 835 over 128.
128. Yep, there we go. So, really gross. Really gross. Rarely in things in life when you have like decimals and they go on forever do they come out to nice round whole numbers. Because every time you multiply decimal by another decimal, it just keeps getting gross. It just adds more and more decimal places. Any questions on these two examples?
No.
Okay. So here, oops, that's supposed to be a plus sign. I think not an equal sign. Easy to do when the plus and equal sign are on the same key. Okay, so this one's a tricky one. It says use summation notation to write the sum. So we have to write it in summation notation, which means that we need to figure out how many terms we have. That's the tricky part. So our summation notation that we want to write this in is I equals 1 to n, a to the 1, r to the n minus 1. The thing is, we don't know what n is because we don't know how many terms we have. So we know that this is a1. We have a2, so those will allow us to get r. We have a3, and then we don't know what term that is. So that's going to be the tricky part here. So first, let's start with r. So I'm going to just take a2 divided by a1, negative 3 over 15, which reduces to negative 1/5. So now what I'm going to do is we're going to use some algebra. We're going to use taking logarithms so that we can determine how many terms we have. Now the book for an example like this says just use guess and check until you figure out what term that is, and I think that's just stupid because that could take forever. There's no reason to have to guess and check when you can actually use algebra to find it. So we're going to take that negative 3 over 625. So we know that this is a1 r to the n minus 1. Some term. We know what a1 is, so I can plug that in. Negative 1, oops, negative a1 is 15. And we know what r is, so I can plug that in. Negative 1 over 5. But we don't know what n is. But we know that whatever you plug in for n, you're going to get that term. So we're solving here. We're going to be solving for n, which means taking logarithms. So the first thing that I would do is divide both sides by 15. So this one I actually worked out ahead of time. And that gives you negative 1 over 3,125 on the left. And then you end up with negative 1/5 to the n minus 1. So now we want to get that n minus 1 out of the exponent. So you can take the log. So you can take a regular base 10 log or you can take a natural log. I usually take natural logs. And I write my natural log in cursive so it doesn't look like a 1n. So we're going to take the natural log of both sides. And then that allows us to use our rules of logarithms to take this exponent and put it down in front. So we're going to have the natural log of negative 1 over 3125 equals n minus 1 times the natural log of negative 1/5. So I want to solve for n, and the easiest thing to do here is to divide both sides by, I could distribute if I wanted to, but I really don't want to. I'm going to divide both sides by the natural log of negative 1/5. So that way I'm just left with n minus 1 on the right. And I'm going to do this natural log stuff on my calculator. And I can pull up the handy dandy Desmos calculator again, and we can do that. So set up my fraction. I think it's under function here. Yeah, so I've got a natural log, negative 1 divided by 3125 over natural log of negative 1/5. Oh boy. Oh yeah, because the natural log, we can't have negatives. I think if I just get rid of the negatives, it should work. Yeah, okay. So we'll just cancel out the negatives. We'll just assume that, because otherwise, yeah, you get some errors there. Okay, so those are going to give us 5. So 5 is equal to n minus 1. So then all we have to do is add 1 to both sides. I get n is equal to 6. So this will allow us to finally write our sum. I equals 1 to 6. And then A1 is 15. And then I don't really need those parentheses, or yeah, I do. R is negative 1/5 to the n minus 1. So that's how you solve this and get the summation notation. When I originally solved this, I had solved it slightly differently when I did this by hand, and I didn't have that negative problem with my natural logs. So I guess I just got lucky there.
Yeah, that's a hot mess.
Yeah, well, you don't have to do any of this on the assignment, but it's a good exercise in what you can do with summation notation. So
it was fun to watch.
yeah, it's a good exercise showing you what just all the variations you can have here. So, but yeah, for the application assignment, you don't have to do anything like this. So that's a good news.
That's good.
Yes. Okay, so now the last thing in this section is sum of an infinite geometric series or sequence, which is what we call a series. So if it goes on forever, we call it a series or infinite geometric series. They're used sort of interchangeable, but the series is basically like when you're adding these things on forever. So that goes to infinity. So it's very similar, but there's a couple things to note how it's different. Is if I rewrite the finite here, Sn, the sum, the finite starts at I equals 1, but the infinite starts at 0. And then the finite has r to the n minus 1. The infinite goes to I. So you can see there's like a sort of an off by 1 error, or not really an error, but like because it's starting in different places, the exponents are slightly different. Sure. And then just as a comparison, the denominators are of their fraction parts are the same. They're still multiplying by A1, but what's different is the top, where for the finite, you're multiplying it, you have a 1 minus r to the n, but you don't have that in the infinite series. So The infinite series is cool because it's a way to add things that go on forever. And you'd think, well, how can you actually get a number? And I don't know how they proved this, but it works. So it's pretty cool that they can figure out what is it going to add to. And just as a heads up, the last question on the assignment is an infinite series, an infinite geometric series. So you'll have to use this formula. So these are just basically practice in using the formula. And so we have n equals 0 to infinity, 2, so that's our a1. We have our r, which is 3/4 to the n. So you're just literally plugging it into the formula. So again, the formula is a1 over 1 minus r. So it's 2 for 1 minus 3/4. And that gives us 1/4. And then that gives us 8. So if you add this up forever, you get 8. On the right, we're going to have to do a little more work. We know A1, but we don't know R. And R, again, is we're going to do the same thing. We're going to take each term. So we have 6 over 9, which is 2/3. So now we know R. So then you just plug it into the formula. 9 over 1 minus 2/3. That's 9 over 1/3. We get 27. So it's actually easier than when you have a finite series.
Yeah.
It's a lot simpler to do. So
you know what my journal gets to be this week? Miss Stephanie taught me everything I needed to know during her class.
yeah. Yeah. So that's basically it. So that was everything that I have, everything that you need to know for the basically what you need to do for the assignment. So I am actually going to pull up my template because I'm going to give you a little hint, and we'll see how many people actually follow this hint if they watch this for the assignment.
That's about as many as show up.
Yeah, we'll see. I mean, I do get more views of the recordings, but certainly not as many as we actually have in the class. So if I can actually get my word to move. Okay. So, whoops, wrong. I have too many things open here. I was trying to find you and I opened the wrong one. Okay. So I'm going to skip down to this one with the bouncing ball.
Oh yeah, I saw that. That one's crazy.
It's not as hard as it seems if you think about what's going on.
How many times the ball's going to go up and down?
It's infinite, roughly.
It can't.
So
The ball will eventually stop bouncing.
It will eventually stop bouncing, but you know, if we assume that it's a perfect world, it will go on forever. So we're dropping it from a height of 6 feet. So it's bouncing down, and then it's bouncing up 3/4 the height, and then it comes back down 3/4, and so on. So we've got a down distance and an up distance going on here. So we're going down 6, but then we're going up only 3/4 of that, which.
So 3/4 is R.
Yes, 6 times 0.75. So that's
this is much easier now that I sat through that class.
So now this is where the tricky thing goes, because we're doubling up, because now we're going down 4.5 again, because it just says the vertical distance, so that's counting both up and down. Mm-hmm. And then we're going up and down again. So you can think of this as 2 separate sequences, or series. You can think of one as just doing the down motions and then doing the up motions and adding those together. Or what some people do is they add these together and then make it one sequence. So for me, that seems more confusing to me. So I separate up as down and up. And then I add my 2 answers. So I have down as 6, and then 4.5, And so our sequence, we're taking the sum and we're going forever. And so we're using that infinite sum where our A1 is 6, and then we have 3/4 of it to the R. We're going to just start counting at 0 here because we're using the infinite sum formula that starts at 0. So it just makes things easier to count at 0 there.
Sure. Now,
we can also do the up. So if you think about the up movements, it goes up. We start at 4.5 because that's the first time it goes up, and then 3/4 of that. So here, oh, that was a terrible sum. Sum I equals 0 to infinity. So our starting point is 4.5.
4.5, 3/4, and yeah.
So if you do it separately as both an up and a down, then all you have to do is use that infinite sum formula for both the ups and the downs, and then add them together, and that will give you your total.
Got it.
So that should be, and when you're showing your work for this, drawing a picture like this is like perfect. So if you like turn in this as your starting point, then that you'll be good showing the work, showing how you came up with formulas, that sort of thing.
Okay, dope.
So that's all I've got. Do you have any questions for me?
No, I got it. Thank you.
Okay. Actually, while I'm here, I do want to clarify something on this number 3 here. Because the total, so the payment, we're paying $250 each time. The unpaid balance does not count interest. It does not include interest. Because the interest, when we have loans, the interest does not go towards our balance. The interest is like the money they're making off of it. So our unpaid balance is not including the interest. So our first day's interest is going to be, it's going to be the, whatever the percent was off of the 5,000, 1%. So that's going to be 50. So your monthly payment is going to be 300. And then you've only paid down 250 out of that 5,000. So that is 4,750. So this payment is going to be the same number. You're always making a base payment of 250, but what's changing is the interest, and the interest is based off of the unpaid balance. So your total monthly payment is also changing, but the unpaid balance is only going down by 250 each time because the interest is not applied towards that. Does it make sense?
Sure.
All right. Okay, that really is the last thing that I have for you.
Thank you so much.
You are welcome. I'm glad that you were able to attend, that you had some free time. So
it was a big help. I learned some things.
Good. That's important. You learned some things.
All right then. Well, I'll try to make your next class. You make them enjoyable.
Good. That's important. If I can make math enjoyable, I consider that a win. So
you're enjoyable. Math is not.
Okay. Well, at least if I'm enjoyable, part of it, there's something there that you're enjoying.
There you go.
All right. Take care.
Have a good one. Yep.
Yeah, you too. Bye.
Bye.